Welcome back. I am so excited to be here, and I hope you are too, because we have an exciting topic today. Okay, now let's talk about this exciting topic. Continuity. All right. Making functions continuous. Now, I hope you guys are already familiar with what it means for a function to be continuous at a certain point. Let's talk about that. Do I have something here? Continuity on closed interval. God, that's disgusting. So, if, okay, so 1 f, let's write that again. So f of x is continuous at x equals c if 1 f of c exists. 2 the limit at three limit just to, can you see that? Okay, so just to brush up on it, f of x is continuous at x equals c if 1, f of c exists, 2, the limit at x approaches c of f of x exists, and if the limit and the value at c both equate each other. So basically, sorry. Oh, wow. That was Can you see that? No, you can't even see that. A whole lot big off. Is that like too big? Yeah, it's a little bit too big. More reasonable? It's definitely more reasonable. So basically what that means is that at C, f of x exists and is right there. And the limit as x approaches c from the negative side points is like equal to that value. Oh man, okay, that's horrible. Alright, I'm gonna move this cursor. Alright, so basically what that means is that f at c, So basically what that means, the value of f of x at c is equal to the limit as x approaches c from the left side and the right side. As you can see here, both sides of them point to this point, and that point is defined on the curve. Okay, a quick and surefire way of proving that a function is continuous at any given point, that point being at c, is to prove that the limit as x approaches c from the negative side of okay. Yeah, right. So a quick and surefire way of proving that a function is continuous at any given point is to do these three steps. To prove that the limit of f of x as x approaches c from the negative side is equal to that as x approaches c from the positive side, and that both those values are equal to the value of f at x equals c. Yeah, this quick and easy way, This is a quick and easy way to prove it, because if both of these exist and equate each other, that proves that the limit as x approaches c of f of x is equal to f of c. Anyway, so let's go back. I'm going to use this little one. Okay. Alright, so the main problem today is going to be trying to make a function continuous. And that would include, I don't know if I want to start off like that. So that's the definition of continuity. Okay, so our main problem today is trying to have a composite function and make it continuous. So let's start off with an example. Okay, example. Find the value a. And the function we have is and ax is fine. Okay, so alright, so we're starting off with this problem. Find the value or values of a that makes f of x continuous on all x. So we have this composite function where from when x is greater to or equal than 1, the function is defined by 3x cubed. Well, otherwise, when x is less than 1, we follow ax plus 5. The first thing to note is that this is a cubic function and then this is a linear function. Alright, so for me, when I was first learning, alright, for me, oof. Okay. So for me, when I was taking calculus my first year, my first instinct was to go, oh, that's easy. Like I can make this continuous because for one thing, it's a polynomial. Both of these are polynomials, and a rule about polynomials is that they are all continuous on all points of x, on all real numbers. So I'm like, yeah, it's easy to make this work. So we can say that 3x is going to be equal to ax plus 5. And then from here, you just solve for a. Oh. Sorry. I'm like, oh yeah, that's easy, because the only point of descriptions that we don't know if they connect is at 1. So basically what we do is we say like at x equals 1, we just say these three are equal. Like just to like see if like it is equal or not. Plus 5. Alright, so we have this when x equals 1 and this when x equals 1. Then we just plug in 1 and see if it's equal. So plugging in 1, we get 1 cubed equals a of 1. A times 1 plus 5, and then solve it. So that's 3, that equals a plus 5. Subtracting 5 from both sides, we get negative 2 equals a. Easy, right? If a equals negative 2, then this function is continuous, right? Wrong. Okay, so this is not a correct way of doing this. This you should not do. Alright. The number one problem with saying this, because this side of the equation is fine to say. because 3x cubed, it's defined at 1. So when we have this function, we can do that. But on the other side, this function is not, like, you're misinterpreting what f of x is. You're saying that at this location it exists when it in fact is not defined by this equation at x equals 1. So we can't do this. The correct way, sorry, okay. Okay, so let's go. Ooh. Okay. So, what is the correct way of going about solving this problem? Well, going back to polynomials, that they are always continuous. That is true. So that first assumption was correct in saying that whatever these are, whatever A is always going to be continuous for those. The only problem that comes that we have to worry about is what happens when x equals 1 at this with this function. Is there a jump? Does 3x cubed stop here and then the other function start here? We don't know. What we have to do is find what happens and define what happens as x approaches 1. So the best way of solving this problem is to go back to the continuous, the definition of continuity. So basically, I'm just going to use the quick and shortened version of it, saying that the limit as h approaches 1 from the negative side of f of x is going to be equal to the limit as h approaches 1 from the positive side of 1. And that's going to, excuse my grammar on how pronouncing limits, I'm very sorry, is going to be equal to f at 1. So I'm just going to say this. For f of x to be continuous, the above statement must be true. If this is not true, then this function is not going to be continuous. So we're going to have to plug in all the information that we know and then solve for a in that way, in that fashion, excuse me. Okay, so let's look at this first part. The limit of f of x as h approaches 1 from the negative side. Okay, so what part of the equation do we want to use? Which equation here do we want to use for this one? Well, when x is on the left side of 1, when it's less than 1, you're going to be using this equation. Because even though it's not at 1, as it's approaching 1 from this negative side, this function f of x is defined by this equation. So when we rewrite this, we're going to use that part of the composite function. Right. Okay. Now let's move on to this next part of the equation. So the limit of f of x as h approaches 1 from the negative side. So how is f defined on the positive side of 1 when x is greater than 1? If you look at here, when x is greater than 1, it's going to be defined by 3x cubed. So that's what we're going to want to plug into this f of x part of it. Alright? 3x cubed. Alright, now for the last bit. How is f defined when it equals 1? Here it's pretty obvious that it's going to be equal, when x equals 1, we're using this equation again. So we're just going to use that. Okay. Now let's solve these problems. Going from this side, because this is a polynomial and technically it's a number over 1, we can solve this limit by direct substitution. There's no problem in doing that. So let's plug in 1 to this equation. So a of 1 plus 5, and that is correct. All right, now let's move on to the next part. It's the same case. This is a polynomial, or a number over 1. So we can solve this limit by, again, using direct substitution. So we just directly sub in 1. Going on to the next part. This is just f of 1, so we just plug in 1 for x. Alright. Now, from this point, we just solve. So we have a plus 5 equals 3. And I'm not going to write equals 3 again, because that is a clear statement. So from here, we subtract 5 from both sides, and we find that a equals 2. No, stop folding. Okay, so wait, what? You're probably thinking, we just found that a equals what we did using the other way. Like, why do we have to use this complicated, convoluted method when there's an easier way of doing it? We use this method because it is the correct way of saying it. The other method, while being simple and, when you think about it, it makes sense. I mean, I always did it. And when I was in high school, it didn't affect any of my grades. As far as I remember, she took it and she was fine with it, mainly because she was just asking, find it, you don't have to prove it. But in reality, mathematics is reliant, in reality, mathematics relies heavily on correct logic. And saying things correctly and not, going some convoluted path to find a correct answer. When you go into your classes, maybe not in high school, but definitely in college, it doesn't matter whether the answer is correct. What matters is that you use the correct method to get there. So if I had done all of this, and at the very last step I said that a equals -5 because I subtracted wrong, that's not so important. You maybe get 1 point taken off, but all the points that were gained were using this kind of logic. And it is important because if you had done it the other way, you would have been saying that f of x is described by this function when x equals 1, when that is not true. Okay. Let's breathe. Okay, so I hope that was an important lesson to you guys about, using the correct path to get to the right answer than going like a bad path to find the correct answer. So what I want to do is do one other problem, but this time instead of finding one variable, we're finding two variables. Okay. Let's see. Analytically. Jesus, please, I don't know if he ever did one. I think he gave us. I'm gonna look up an equation because I don't have one. Well, my computer's loading because it's being slow. Let's do this. I'm gonna ask me why he's making that face. It's really funny. I wonder if it's paused. Is it still going? Alright, so we have this new equation. Well, we have to find two variables, a and b, using this equation. Okay, so f of x, using this equation. F of x is defined as when x is less than 1, f of x is equal to 2ax plus 5, and when it's greater than or equal to 1, it's defined by 3x minus b. So let's go back and try using the definition of continuity to find this problem. Okay. Alright, so again, since both of these are both polynomial lines, the only thing we are concerned about is what happens at x equals 1, whether the two lines intersect. So I wrote this out again, the limits on either side of 1 and f of 1. So let's continue. So when x is less than 1, as it's approaching 1 from the negative side, we are going to be using this force equation. So let's plug that in. Alright, and then when x is approaching 1 from the positive side, we are going to be using the other part of the equation. And let's plug that in. Alright, and then when f equals 1, we are going to be using that equation again. Alright, and then when f equals 1, we are going to be using that equation again. Alright, and then when f equals 1, we are going to be using that equation again. Alright, and then when f equals 1, we are going to be using that equation again. Alright, and then when f equals 1, we are going to be using that equation again. Alright, and then when f equals 1, we are going to be using that equation again. Alright, and then when f equals 1, we are going to be using that equation again. Alright, and then when f equals 1, we are going to be using that equation again. Alright, and then when f equals 1, we are going to be using that equation again. Alright, and then when f equals 1, we are going to be using that equation again. Alright, and then when f equals 1, we are going to be using that equation again. Alright, and then when f equals 1, we are going to be using that equation again. Alright, and then when f equals 1, we are going to be using that equation again. Alright, and then when f equals 1, we And this time I'm just going to plug in 1 right away. Alright, so now we solve these limits. These are both polynomial equations with a numerical value over 1, so we can just solve the limits by direct substitution. And by doing that, that's going to be equal to 3. Alright, now we're going to simplify. Alright, and then we come up with this equation. Because this is a 2-variable equation, it's important that we have 2 sets of equations. So this is going to be equation 1. Yeah, what I'm going to do is actually just isolate one of these variables and then write it here, and then we're going to try to find another set of equations to use. Alright. Yeah, I mean, I think that would be easiest. So we have this equation already. Now the question is going to be, what are we going to use? I think what I want to do is find the derivatives. Okay. I remember doing this in class. I don't know why I can't find my notes for it. Alright, so now we have it. We have this equation of what b is equal to in relation to a. Now we have to find another set of equations that we can use to help find a and b. Because this will not suffice, this relationship. We have to find a specific a and a specific b. Alright, so what can we do with this? I am thinking that we can actually find the derivatives. We can make an equation set of this and see what we get. Well, the question is, blah. Well, probably is like a sharp point, so I don't know. Let me find my notes. I don't know what happened to my notes. Actually, you want to continue to do this? That's the problem. I'm just gonna say like that. whole question. Alright, actually, I've changed my mind. I'm gonna do a different problem. That's too hard. I'm not sure how to do it. Alright, so now we have this problem where we have to find an A and B that makes this function continuous. And so what I want to do is obvious. Well, I shouldn't say that. Okay, so the first thing to note again is that all of these functions are polynomials. This one's a constant, so it clearly is continuous on all on all x. And then both of these are, oh shit. Wow, okay. Excuse me. Yeah, that probably is what it was. Okay. Alright, so we have another example, this time with two variables that we have to find. So we have to find an A and a B such that it makes this function continuous on all of x. And so the first thing to note is that both of these are polynomial equations, are actually straight lines. So we know that they are, like, by themselves continuous on all x. On all x, and we also know that 5 is a constant that also is continuous just by, like, looking at its graph and knowing about it. It is continuous on all real numbers of x. So let's begin with this. The one problem that we are unsure about is what happens when x equals 1. Because we know what it equals when it's 1, but what actually, like, what happens with these? These all have to be continuous at one point, 1. So we have to use, again, the definition of continuity. So I'm just going to write that out right now. Alright, so now we have this equation again, and now we just plug in f of x and all the necessary values. So the limit of f of x as x approaches 1 from the negative side. So we look at where f of x is defined on the negative side of 1, and that's clearly when x is less than 1. So we'll be using this part of f of x in this equation. So let's write that out. The limits of x approaches the side of 2ax plus 5. Alright, and we do the same thing with the other side. When is f defined? When x is on the positive side of 1. So when it's greater than 1. And when it's greater than 1, it's defined using this equation. So we're just going to go ahead and plug that in again. Alright, lastly, when is f defined at 1? Literally at 1, not approaching 1 from the negative or positive side, but right on 1. And looking at this equation, it actually is easy to see that when x equals 1, it equals 5. So we just plug in that equation, which is pretty easy, 5. Alright, now we solve these limits. Again, looking at both of these again, they are both values over 1, so we can go ahead and just solve the limits by direct substitution. So let's plug in 1 to both of these equations. All right. Now let's simplify. Okay, so from this we can derive two equations. One equation is that 2a plus 5 is equal to 5. Another equation that we can make is that 3 minus b is equal to 5. So now what we will want to do is isolate a and b and figure out what these values are. And that's what I'm going to do right now. So okay. Okay, so we found two values. A is equal to 0 and b is equal to -2. These values have to equal these so that this function is continuous on all of, on the whole domain. That is this, from -infinity to +infinity. Alright, so we can go ahead and try to check that by graphing it. The new equations. Okay. Oh. I'm actually going to do it again. Okay, so alright, so we have alright, so we have this first equation. Second equation. Then we have the third equation, where starts here at 2. Oh. Dang. Oh, look, it's moving. That's no good. You can't see what that says. Private. I messed up on my scaling. Okay. I should pause this. Still. We'll do this again. Okay. Alright, so when I graphed it, or rather when I plugged in the values, I found that when x is less than 1, the function is going to be equal to 5. When it's at 1, it's also going to be equal to 5. And then when it's greater than 1, it's going to follow the equation 3x plus 2. When you graph this, you find that this goes all the way to negative infinity until it approaches 5, but does not equal 5. However, the next equation actually fills in that circle, but only at that point. Then the last equation, 3x plus 2, when it's graphed, it goes straight from 5, like it's not equal to it, but approaches it, and it goes all the way to infinity. So that shows that this problem is continuous. This is why I did it in here. Let's get short again. Alright, that's a wrap. That's all I have for you guys. I hope you were able to learn something about the importance of mathematics, and hopefully maybe got some help on getting ideas about how to solve any problems that you might get in school. I'll see you guys again.